Hello and welcome to the video about cyclic quadrilaterals, which details the properties of theorem 13 and 14. If something is cyclic, then it is inscribed inside a circle just touching the circumference. So this video is about properties of four-sided shapes whose vertices are on the circle. If you have a cyclic quadrilateral, then the opposite angles are supplementary. So we are going to attempt to prove two things for this theorem. The first is that angle ABC and angle ADC add to 180, and you can see them labelled there on the diagram. The second is to prove that angle BAD and angle BCD are also equal to 180 degrees. We know that the quadrilateral is cyclic. Again, this means that the vertices are points on the circumference. We are going to join OA and OC together to use in our proof. To begin, we note that angle AOC is two lots of angle ABC because angles at the center are twice the angles at the circumference. Similarly, the reflex angle AOC is twice the angle at ADC. But the two angles at the center will add to 360 because the angles at a point add to 360. Therefore, two lots of angles ABC and two lots of angles ADC will also equal 360 degrees. So if we divide this expression by 2, we get the angle ABC plus angle ADC equals 180 degrees, which was our first aim. Now we can say that all the angles in this quadrilateral will add to 360. I've named them all using the three-letter convention instead of just saying angle A or angle B because I want to be clear about the angles that I'm talking about, and you should too in exam situations. We can now say that the two remaining angles BAD and BCD also equal 180 degrees, which was our second aim. If you can't see why that is so, it's because we have subtracted the 180 degrees from the two angles we proved from our first aim. We will now look at an example which will use this theorem. Example 10 gives a diagram and says if angle DAC equals 45 degrees, and angle BAC equals 35 degrees, and angle ABC equals 85 degrees, find the values of x and y. Take a minute to draw the diagram and attempt to find the values for yourself giving reasons. While this question doesn't specifically state to give reasons, in this topic you're always expected to, regardless of what the question says. This might seem confusing, but it is always better to give reasons and be wrong, and not give reasons and be wrong, because you can be given marks for part answers. Begin by noting to yourself that ABCD is a cyclic quadrilateral, which means that the opposite angles are supplementary. I start my proof by stating the sides of angle DAB, by adding 45 and 35 together and getting 80 degrees. I now say that angle DCB equals 100 degrees because opposite angles in a cyclic quadrilateral are supplementary. I can say now that angle ACB is 60 by using the angle sum of a triangle property. This lets me say that DCA equals DCB minus ACB, which means that x equals 40 degrees. I can also state that y equals 95 degrees because opposite angles in a cyclic quadrilateral are supplementary. This was not the best way to prove what x and y equals. It would have been quicker to start with y equaling 95 degrees, then using the angle sum of a triangle property to prove that x equals 60 degrees. I did it this way to use our new property twice instead of just once. Both ways are accurate and will give full marks as long as the reasons are logically set out. The 14th theorem lets us know that the exterior angle of a cyclic quadrilateral equals the opposite interior angle. Our aim is to prove that the exterior angle BCE is equal to the opposite interior angle BAD. We know that ABCD is a cyclic quadrilateral and that DC is produced to the point E, creating the exterior angle. To start our proof, we will let angle BAD equal x. We can therefore say that BCD is 180 minus x because the opposite angles in cyclic quadrilaterals are supplementary. We also know that angle BCD and angle BCE will equal 180 degrees because DCE is a straight line. Therefore, 180 minus x plus the angle BCE equals 180 degrees. Therefore, angle BCE equals x. And therefore, angle BCE equals angle BAD because both are x. I could have possibly stopped at the line beforehand, but I think it's important to end it with a restating of the aim as the final line of your proof. Sort of like saying you started out wanting to prove something, and now you have. We'll end with two examples which will illustrate the use of the theorem. Example 11 says the two circles intersect at A and B. PAQ and XBY are straight lines through A and B that cut the circles at PQ and XY respectively. we are to prove that PX is parallel to QY. Take a minute to pause the video and attempt this for yourself. A hint would be, when proving something is parallel, you can either show that the corresponding angles are equal, alternate angles are equal, or that the co-interior angles are supplementary. Okay. Our aim is to prove that PX is parallel to QY. We know the two circles intersect at A and B, and PAQ and XBY are straight lines. We will need to join AB to help with our proof, as well as producing AP to the point R. This will create an external angle RPX. I start my proof by stating that PABX is a cyclic quadrilateral. With this comes all the properties of cyclic quadrilaterals. This means I can use the fact that angle RPX equals angle ABX because the exterior angle will be equal to the interior opposite angle. I've put my reasons in blue for this example to make them stand out a little bit better. Similarly, I can state that QABY is also a cyclic quadrilateral, meaning that angle ABX is equal to angle AQY for the same reason. I have now shown that angle RPX is equal to angle AQY, which means that PX is parallel to QY because the corresponding angles are equal. Example 12 looks a bit like a dog's breakfast of lines in a circle. It says that ABCD is a cyclic quadrilateral and AB is produced to E. The bisector of angle ADC cuts the circle around ABCD at F. We are to prove that BF, produced if necessary, will bisect angle EBC. What a mouthful. Look, pause the video and reread the question, making sure you understand all the terms used and where on the diagram they sit. Try and get as much of the proof done as possible with reasons. You should begin by locating the angles you are to prove are equal. Okay, our aim is to prove that angle BF bisects angle EBC. This means we're going to show that angle EBF equals angle CBF. We know that ABCD is a cyclic quadrilateral. AB is produced to E, and DF bisects angle ADC. I start my proof by stating that angle FBC equals angle CDF. This is because they are angles in the same segment. Angle EBF equals angle ADF because the exterior angle of the cyclic quadrilateral FBAD is equal to the interior opposite angle. But we know that angle ADF equals angle CDF because DF bisects angle ADC from our data. Therefore, angle FBC equals angle EBF, which means that BF bisects the angle EBC. Our next video in the series will show the tests for cyclic quadrilaterals. Thanks for watching.